Good morning. So now let's quickly look through chapter number 25. Okay, the first part that madam has already taught, but which I'm told that most of you have not attended. So that's the reason why I thought I'd do it. So you can see that the title of the chapter is 25, and you can also see that this chapter is going to be okay the basis for the rest of the chapters that are coming. Okay, so now before we get into the chapter, I have to ask you a question. If you look at any book on electromagnetism, even starting from your school days, you would have seen that electric force and magnetic force will just figure in only one chapter each. After that, what happens is, you will be talking about electric field and magnetic field, your Ampere's law or your Gauss law or Faraday's law. If you look at any of the laws, you will see that magnetic or electrostatic forces don't figure there. It is only the electric fields that figure. So here is a question for you. Why does electromagnetic force form the basis for our study of electromagnetism? If we are going to not discuss force at all at a later stage, why should we begin with force? Okay, I'll just try to answer the question. The simple reason is that, field is a concept that is used to understand how two charges which are not in contact with each other are exerting a force on each other. It's okay. You can understand physical forces. Like somebody is here, somebody comes, gives a push. It's a physical push. There is an effect. Okay. But then you can't understand how two charges which are not touching each other, they're not in contact with each other, how they are exerting a force on each other. So to understand and explain these things, this concept of fields have evolved. Okay. So field is an imaginary concept. Okay, but force is something that you can actually see. Field is abstract, but the effect of field on a charge is force. And force is something for which human beings have a physical intuition, and you can actually see the effect of force. Okay, so that's the reason why all chapters, all these books start with forces. Now, when you talk of force, what are the four forces? Let's quickly see. All forces, I'm not getting into the unification of force, the grand theory which unifies force. I will simply talk about the four basic forces right now. The four basic forces are gravitational, okay, and the next is electromagnetic force, which is what we are going to study in this particular semester. Then comes the weak forces. So what are these weak forces? They are responsible for your radioactive decay. You know that alpha particles, beta, gamma, these are all the effect of radioactive decay. Okay, so it's these weak forces that are responsible for the instability of certain nucleus, which can decay and form smaller elements and then in the process radiate energy or radiation. And then the last type of basic force that you will see is the nuclear force. This, as the name itself suggests, it's called a strong force also. Okay, why it's called strong force, we'll see a little later. It is this force that keeps the protons and the nucleus within the nucleus of an atom. You know that within the nucleus of the atom you have protons and nucleus. Neutrons. Neutrons don't have charge, all right, but then protons are having charge, and you all know that like charges with the same signs will repel each other. But you are able to put together so many protons within the nucleus and it is not repelling and coming out. Okay, so there is a force called nuclear force, which is stronger than your electromagnetic force, which is operating within the nucleus. Okay, so this is the fourth force. More about this we will see as we go along. Then, if you look at how these forces operate, where do these forces come into picture? You can see that gravitational force is a long-range force. It is a long-range force, meaning you can see between galaxies, between your planets, sun and the planets, etc. Okay, and you can see that it follows the 1 by r square uh, formula, meaning F is equal to capital G m1 m2 by r square. So it follows that 1 by r square dependence. Now come to electromagnetic force. This is also a long range force. Long range force, it can operate over meters. Okay, again, this also follows the 1 by r square formula, where the gravitation electromagnetic force is given by F is equal to K Q1 Q2 by r square. So Coulomb's law. So there also 1 by r square dependence is there. Then let's come to the weak force. Weak force, if I remember telling you, it is actually the force responsible for radioactive decay. Okay, these are short range forces. These are short range forces. They operate at the level of around 10 to the power of minus 18 meters. 10 to the power of minus 18 meters, which is very, very small. Okay. Now let's go to strong force or the nuclear force, which is responsible for the stability of the nucleus. Okay. So that would be having short range. That means they operate only for that kind of length. For anything greater than that distance, they don't operate. Okay. They operate for ranges of 10 to the power of minus 15 meters, which is what you call as a femtometer. And do you know what is this 10 to the power of minus 15? This 10 to the power of minus 15 is an interesting number actually. 10 to the power of minus 15 is actually the radius. 10 to the power of minus 15 is actually the radius of the nucleus. That means within the nucleus, this force will operate for that distance. Then come to 10 to the power of minus 18, which is for the weak forces. So where is that? That is still smaller at the particles, at the basic particles, subatomic particles, not even subatomic particles, like you're talking about quarks, muons, etc. Okay, at that level, when you are dealing with particle physics, at that level, these weak forces will operate. Okay, and this relative strength between two protons. So here, what he has done is, the author has taken two protons and then talked about uh, typically protons would have distances which are of the order of nanometers. So if you take two proton, or we are talking within the atom, okay. So when you're talking within the nucleus of an atom, and if you're talking about two protons, then only the nuclear force is strong. That is within the nucleus. So the nuclear force is strong. So if I take that as relative one, then in comparison, the weak force will be weaker by over 10 to the power of minus 7 magnitudes. Then you look at electromagnetic, which is stronger than weak force. It is 10 to the power of minus 2 at that range. And the gravitational force is very, very small. It will be 10 to the power of minus 38 in comparison at such distances. So that's the reason whenever you're doing any problem dealing with elementary particles, when you're dealing with charges, you don't take the mass of these charges and do a calculation. That's because gravitational forces become very, very negligible at that distance. Okay. So now with these words, let me just go ahead and talk about. You must remember that we are dealing with electrostatics. The first few chapters will be on electrostatics. Electrostatics means charges are not going to move. So we are dealing with objects where charges don't move. Okay. Typically, what are those objects on which charges will not move? They are insulators. Or first what we do is we'll make a comparison between insulators and conductors. The finest thing that all of you, the basic thing that all of you know is that insulators do not conduct electricity, whereas conductors will conduct electricity. So that automatically means that insulators don't have mobile charges while conductors have charges which can move. Maybe free electrons in the case of a conductor, a metal, or it can be ions which are moving in the case of, let us say, an electrolytic solution. Then let's go to the third important property of insulators. So what happens is, if I have an insulator, within the body of the insulator, let's say it's negatively charged, within the body of the insulator, the charges can reside, or there is a volume charge distribution. We are talking of electrostatics. Okay. Now, when you're talking about a conductor in an electrostatic condition, that is when the charges are not moving, then there what happens is, if you're going to have a conductor and if it is negative charge, the charges will reside on the surface only. The charges will go and sit on the surface. There will be no volume charge. There is no charge inside. Okay. And the next thing is, if I have an insulator and if I bring another charged object near it, a charged object near it, this distribution of charges remains undisturbed if it is an insulator. Whereas if it's a conductor, let's say I'm going to bring a positive charge body, then what happens is all these negative charges will move. They will all move and start accumulating here. The negative charges will start moving. Sorry, I'm making a mistake here. Let me just correct it. Let me just correct it. Positive and negative charges will actually attract each other. Okay, so let's just draw a picture. So what happens is if I'm going to have an object which is negative charge, the negative charges which were initially distributed uniformly on the surface will all start getting attracted towards the positive object. So what happens, there will be an accumulation of negative charges here. In that sense, there is a movement. Okay, so the charge distribution is getting disturbed. Then finally, I will simply sum of all these things that I have discussed. So insulators don't have charges which move. Okay, there is no conduction of electricity. There is a volume charge distribution, and this distribution will not get disturbed by the presence of other charge bodies around it. And in the case of conductors, everything is opposite. Now let's go ahead. Okay, now comes the hero of the chapter. So this is Coulomb's law or electrostatic interaction. So as the name itself suggests, you're talking of two charges which are interacting with each other. Interaction means what? Force. One is exerting a force on the other. Okay. So this was idea of Coulomb in 1770. So let's see a concise, beautiful statement of Coulomb's law. So it says that the electric interaction between two charged particles. So remember, he's talking of particles. Particles means which can be treated as dots, not having a volume. Okay. So if you take two charged particles which are at rest, condition is they are at rest or at best moving very, very slowly with respect to each other, then the force between them is directly proportional to the charges of the two bodies and inversely proportional to the square of the distance between them. Okay, and it also says that the direction of the force is a vector. It is what a direction. The direction of the force will be along the line joining them. Okay, so let's see what mathematically this means. Mathematically, this means that F is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. What I will be doing here is I will not be using this F every time. Okay, I will not use this F every time. Like I won't be using this 1 by 4 pi epsilon naught every time. I will write it as a constant k into q1 mod q2 mod divided by r square with an r cap. Okay, let me explain what this means. Mod q1 and mod q2 are the charges of the two bodies without taking the sign. Even if it is negative or positive, take just the modulus. Next, 1 by 4 pi epsilon naught is a constant, it is k. And k value is equal to 9 into 10 to the power of 9. Okay, that you should remember. The next thing is you have an r square dependence. That means if I have a positive charge and let's say I have another positive charge carrying charges q1 and q2. And if the distance between them is r, then you can see that these two are going to exert, or let us talk about what is happening to one because of two. It will experience a repulsive force, right? It will experience a repulsive force. So you can see that the force is along the line joining these two charges. It is along the line joining these two charges. Okay, so you can write it as k into q1 q2 by r square with this r cap giving the direction. And what is r cap? R cap is a unit vector in the direction of r. So if I say that this is my r vector, then r cap is going to be r vector divided by modulus of r. Okay, modulus means magnitude of the r vector. So I hope you understood now. Coulomb's law says that the force is proportional to the product of the two charges and inversely proportional to the square of the distance. And it is along the line joining the two. Even if it's an attractive force, let's say one of them is negative, then also it will be along the line only. Maybe the force direction is opposite to the r vector. That's all. Okay. And the condition is that you are talking about charged particles will behave as particles and they should be at rest. Okay, so that's all. So we have to discuss all these things that we have discussed at rest or very slow relative motion. Why are we putting this condition? You must remember that we are talking of electrostatics. Electrostatics, not magnetostatics. You know that when a charge moves, when a charge is moving, it is current. And currents create magnetic field. So you're not talking of magnetic field here. You're talking of only electric field. You're talking of electrostatics. Therefore, the charges have to be at rest or at most slowly moving. Next, pieces R. What can be the values that R can take? That's the next question. So please remember, R can range from 10 to the power of minus 15 meters to R tending to infinity. Why this 10 to the power of minus 15? Because already we discussed what is called the nuclear force. Outside the nucleus of an atom, this force operates. Inside the nucleus, which is the force that will operate? It is the nuclear force that operates. So this force, electrostatic force, can start from this place all the way to infinity. So that's the range of R. Next, is there anything about the size of the charge? We said it has to be a particle, but is there any condition about the size of the charge? For that, what I will do is I will just take you to page number 573 of your book. Okay. And if I go to please, the soft copy of the book is made available to you. Kindly use that. So let's go to 573. So what does 573 say? Okay, 573 says that this equation holds only for charged objects whose sizes are smaller or very small when compared to the distance between them. That means you can't talk about two spheres, which are touching each other like this, two spheres like this. Okay, because here what happens is the distance between them is smaller than the size of the object. Okay, so what is the condition? The charge particle should be point charge particles. That means their size should be very small when compared to the distance r. So that is the condition. Next, validity of principle of superposition. Principles of superposition we'll be discussing. Okay, so then I will discuss that. Then finally, what is this 1 by 4 pi epsilon naught? What is the significance of this 1 by 4 pi epsilon naught? Please remember that whenever all electrical equations will have 1 by 4 pi epsilon naught and all magnetic equations will have mu naught by 4 pi figuring. Okay. And I already told you 1 by 4 pi epsilon naught is 9 into 10 to the power of 9. Then why not keep it that way? Why should you write this in terms of this complicated number? Why should you write it as 1 by 4 pi epsilon naught? And you know the value of epsilon naught. Epsilon naught is 8.85 into 10 to the power of minus 12. So why at all remember such a thing? It's difficult to remember. But it is not done without any reason. There is a reason. Epsilon naught is an electrical constant talking about the electrical property of the medium. When you talk of magnetic equations, magnetic force, magnetic field equations, you will find mu naught. One is permittivity, the other is permeability, that's all. So both are talking about the property of a medium and how the medium is going to behave when there is an electric field or a magnetic field. And more than this, there is one more connection between them. What is that connection? Let us see. Okay. I hope you remember that the speed of light is 1 by under root of mu naught epsilon naught. So that's a connection. Okay. And what is light? Light is an electromagnetic radiation. It's an electromagnetic wave. An electromagnetic wave will have an electric field and a magnetic field perpendicular to each other. So that's a connection between electric field and magnetic field. And I am telling you, electric field and magnetic field are separate from each other, are independent of each other only in electrostatics or magnetostatics. Magnetostatic, when we come there, I will explain. Electrostatic, now you understood. Okay. So whenever there is electrostatics, there is no magnetic field. Electric field and magnetic field are separate from each other. But Whenever you have moving charges of current, then electric field and magnetic field become inseparable from each other. And a typical situation is radiation. Radiation is electromagnetic waves. Okay, so that's why all your electromagnetic equations will have this 1 by 4 pi epsilon naught and mu naught by 4 pi. Okay, then is this exponential really 2? Yes, this exponential is really 2. It is not, the exponential means which one? 1 by r square. That is 2. It is not 2.1 or 2.0001. No, it is 2. How do you know it is 2? We know it because people have done experiments and then found out that it is true. Okay. Now, let's just go ahead. Here, I want you to just go through this yourself. I'm not going to discuss this. You know that electrostatic force and or Coulomb's law and gravitational law both are very, very similar to each other. So what I've done here is I've just put together the points comparing electrostatic force and gravitational force, because when you go through this, then your understanding becomes better. So that's the reason why I've done it. I'm going to ask you to go through this yourself. Okay. Only thing is maybe I will just discuss one or two things here. Okay. Like for example, there are some problems which we have to discuss. Okay. I will just discuss this problem and then give you the reason why we are discussing these problems also. Let me do that. So I have to go to some empty slide. Let me see whether I have some empty slides. I thought I made some empty slides. Yeah, here I have some empty slides. Okay. So what I'll do is I'll just work out some problems, okay, some important problems. And they are actually teaching us some physics. Let us see what's the first problem. It's a sample problem. Sample problem 2. I will start with, let's say, sample problem 1. Okay, sample problem 1. Sample problem 1 is talking about a penny. You know what's a penny? Penny is a coin. Coin. It is electrically neutral. That means it has got equal number of protons and electrons. And what will be the magnitude of these charges? This is not really a problem. It is just trying to find out how many electrons are there in a coin. Okay, so the author just uses some chemistry formula and then he arrives at some number. He says that there will be, okay, I'll write the answer straight away. There will be n equal to 2.95 into 10 to the power of 22 atoms. So that means you can find out how many electrons and protons will be there for copper. And this is copper, let us say. You know the atomic number of copper, so you know how many electrons and protons will be there. So from that you can find out how many electrons and protons are there. Then you know that each electron or a proton will have a charge equal to 1.6 into 10 to the power of minus how much? 1.6 into 10 to the power of minus 19 coulomb. So you can actually find out the total charge of the electrons equal to total charge of the protons. Please remember, I'm not taking minus there because I'm just taking the magnitude. Okay, the total charge of the electron is equal to total charge of the protons present, and he calculates it to be 1.35 into 10 to the power of 5 coulomb. So that's the total charge, he says. Okay. Then he says that this is the number, but then the entire entity is neutral, so they are able to exist at the atomic level, and you are able to have so many electrons within an atom. Okay. Instead, if you want to charge this coin, how do you charge the coin? You may rub the coin maybe remove some electrons, then it becomes positively charged. But if you see what is the charge of any body, you would always see that it is nanocoulomb, microcoulomb at most. You never see coulomb. You never see coulomb because you cannot actually disturb the charge neutrality beyond a certain level. This comes from chemistry also. You know that to remove the first electron from an atom doesn't require much energy. But the second one, requires much more. Third one, much, much more. So removing or adding electrons can be done only in small numbers. Therefore, the charge of any object cannot be very large. It has to be small. So that's the take home from this particular problem. This is sample problem 1. Okay. Now, I would also like to go to some sample problem 2. Okay, sample problem 2 is, because it's sample problem, I'm not really writing down the questions and all that. So bear with me because I am doing something that I was not supposed to do at all. Madam has taught you all this, but still you people have not attended classes. Okay, so what does sample problem say? 2 says, let us say that you are able to separate out. I told you how difficult it is already. Okay, but let us say that you are able to take out all the protons separately and electrons separately for this coin. Okay, so that means QE equal to QP equal to 1.35 into 10 to the power of 5 coulomb. Let us say you are able to separate out. You cannot really do it, but let us say you are able to separate out. And you're separating them and making them into 2 bundles, and then you are placing them at a distance 100 meters from each other. Okay, then the author is asking you to find out what will be the electrostatic force of attraction. Electrostatic force of attraction, 1 by 4 pi epsilon naught q1 q2 by r square. So let's just do it. So 9 into 10 to the power of 9 into Q1 is going to be 1.35 into 10 to the power of 5. Same with Q2. So I will put a square there divided by 100 square. Okay. So when you do this calculation, you find that the force is, believe me, the force is 1.69 into 10 to the power of 16 Newton. Force unit is Newton. So what is 1.69 into 10 to the power of 16 Newton? That's enormously large. You know that the weight of a 100 kg fat man will be 100 into 9.8, which is 980 Newton. Okay, then think of this 10 to the power of 16. That's very, very large. Okay, so what does this author say after making this calculation? He says that in doing this calculation, we have sidestepped the problem of forming such a bundle. We cannot in reality form such a bundle. Okay, why we cannot do that? Because you know that it requires enormous energy to knock out even 1 or 2 electrons. So think of separating out all the electrons from an atom. You cannot do it. Okay. So he says that, first of all, you cannot do it. The next thing he says is, even if you can do it, can you bundle so much of charge together? Can you bundle all the positive charges together? Can you bundle the negative charges together? He says, no. They would simply blast apart. You cannot bundle such a lot of charge. They will simply blast apart because of the mutual force of repulsion. So what is the lesson from this particular problem? It says that you cannot disturb the electrical neutrality of ordinary matter very much. That's the reason why the charge of any body can only be in terms of nanocoulomb or at most microcoulomb. You cannot disturb more than that. You can knock out a few electrons or add a few electrons, not more than that. Okay. So what happens if you try to pull out more electrons? If you try to pull out a larger amount of charge contained in a body, a large Coulomb force will appear automatically and pull the electrons back. So you cannot remove. Okay. So we have discussed 2 numericals. Please, I'm not writing the questions intentionally. That's because I want you to go through this yourself. Go through the book. Now let's go to this third problem. So what does it say? The average distance r between an electron and proton in the hydrogen atom. So we are taking sample problem 3. So we are talking of hydrogen atom, and it says that in a hydrogen atom, the average distance between an electron and a proton in a hydrogen atom, the average distance r is 5.3 into 10 to the power of minus 11 meters. Can you see here that it is much larger than 10 to the power of minus 15? So that means electron is outside the nucleus. Okay. So now what is the force of attraction between them? Straight away you can do it as 1 by 4 pi epsilon naught. Charge of each of them is 1.6 into 10 to the power of minus 19. I will simply square it because I don't have to put a minus because I'm only talking of magnitude, divided by r square, 5.3 into 10 to the power of minus 11 whole square. Okay, so how much is it coming? It's coming to 8.2 into 10 to the power of minus 8 Newton. 8.2 into 10 to the power of minus 8 Newton. Okay, so what does the author say? He says that although this force appears to be small, this may appear to be small, okay, it can produce a huge acceleration on an electron or a proton. It can produce a huge acceleration. Because after all, you know that F is also equal to m into A. And what is the mass of an electron, for example? The mass of an electron is 9.11 into 10 to the power of minus 31 kg. Okay, and you left side you put 8.2 into 10 to the power of minus 8. Okay, from this you can see that the acceleration A is very large, very large. So even such small forces are sufficient to create a large acceleration simply because of the size of the charged particles. Okay. Next, what you're expected to do is the next part of the problem is find the find the gravitational force between this electron and proton. So what do I do? If G equal to capital G m1 m2 by r square. So let's just put the formula. I put the formula. Let's put the value of G, universal gravitational constant, 6.67 into 10 to the power of. My God, I'm doing a bad job. Into 10 to the power of this is 10 to the power of minus 11, and the mass of an electron is 9.11 into 10 to the power of minus 31, and the mass of a proton is going to be 1.67 into 10 to the power of minus 27, obviously much greater than 3 orders of magnitude greater than an electron. And then what about r square? R, the distance we have taken as 5.3 into 10 to the power of minus 11. So let's square that. So when you do this problem, the answer you get for gravitational force is 3.6 into 10 to the power of minus 47 Newton. Now compare this and this, and you will see that the gravitational force in comparison is much weaker. It is much weaker. You can see that it is about 10 to the power of minus 38 times. It's 10 to the power of minus 38 times the electrostatic force. Okay, the reason why I did this problem is because if you just go to the previous slide, one of the previous slides, yeah, you have seen here, not 10 to the power of 38, it's 10 to the power of 36. You can see that the electrostatic force is 10 to the power of 36 times stronger than gravitational force at atomic scale distances. So that's what comes from this particular. Okay, and similarly, look at this sample problem 2, which we did told you that creation of large forces is impossible for electrostatic forces. Why? Because you can't have large Q1 and Q2. Therefore, you cannot create large electrostatic forces. But when you come to gravitational force, what happens? Any size of mass you can have. That's why you have your Jupiter. That's why you have galaxies. Therefore, you can have large gravitational forces. But when you come to distances which are of the atomic level, interatomic level, there the gravitational force becomes very, very weak. It is 10 to the power of minus 36 times the electrostatic force. I hope this point is clear. Okay, now that we have done with all this, let's just go straight to Coulomb's law in the vector form. So talking of Coulomb's law in the vector form, okay, so here, look at this. I have a charge Q1, I have a charge Q2. And I'm talking about what is going to happen to 1 because of 2. So that force is F1, 2. And if I assume that both of them are having the same sign, then there is a repulsive force. So what is going to happen to Q1? Q1 is going to get pushed away from Q2 and the force is F1, 2. Now, where is 1 with respect to 2? 1 is respect to 2. With respect to 2, 2 is like your origin. This position vector is R1, 2. Okay. Now I write R cap. What is R cap? R cap is the unit vector in the direction of R1. I did all this in a few slides back. A few slides back I have done this. I didn't write R1 to I just wrote R. But then here now we are specifically talking about what is going to happen to 1 because of 2. So you use this notation F12. When I write F12, it means force on 1 because of 2. Okay, that's given by 1 by 4 pi epsilon naught. Mod Q1 mod Q2 divided by R12 square. Okay. Now why do I put mod Q1 and mod Q2? Even if they are negative charges, I will put mod. That is because it is not the sign of the charges which will mathematically get into this expression. No. Okay. That is not what will get into the expression. The direction of the force is given by this mod R12. It is given by mod R12. So you don't have to put the minus here. Okay, now look at this. Mod R12 is parallel to F12. Therefore, I can say that F12 has the same direction as mod R12, where R12 is the position vector of Q1 with respect to Q2. Q1 with respect to Q2. Q2 becomes your origin. And you can see both these vectors are parallel to each other. Now, if on the other hand, you have one of them positive and the other one is negative. Okay, now what will happen? You're again interested in F12. Again, write 1 by 4 pi epsilon naught Q1 Q2 by R12 square mod Q1 mod Q2. Okay. But now you look at what will be the force on the positive charge. Positive charge will get attracted. It will get attracted. Or you're finding that F12, okay, F12 is anti-parallel. It is anti-parallel to R12. Okay, therefore, when you're writing the equation, it becomes F12 equal to minus 1 by 4 pi epsilon naught mod Q1 Q2 by R12 square into R12 cap. This minus is coming because they are anti-parallel. Or you will see that all attractive forces, even in gravitational, you must have seen, will have this minus sign. And this minus sign is coming because of this discussion only. Next, if 1 is experiencing a force because of 2, 2 can experience a force because of 1. Okay, so what will you call that force? You will call it as F21. And then when you're writing F21, you should talk about R21. Talking of 2 with respect to 1, 1 becomes the origin. Okay, so you can see that the third law is automatically obeyed here. F12 will be equal to minus F21. So it's not difficult for you to write those equations. Only thing is when you're writing F21, write in terms of R21. That's all. So we have seen how to deal with Coulomb's law in the vector form. Next thing is, why are we dealing with Coulomb's law in the vector form? It's difficult. Why should you write instead just write 1 by 4 pi epsilon naught Q1 Q2 by R square? Why should you have this vector form? That's the next question. You have to deal with vectors because vectors give you a lot more information than scalar equations. And next thing is we have to apply the principle of superposition. What is principle of superposition? If I have a collection of point charges Q1, Q2, Q3, Q4 at rest, and I want to know what is happening to Q1 because of Q2, Q3, and Q4, then principle of superposition says that the net force on one will be equal to the forces that each of them exert on Q1 separately. Take the force that each of the other three charges will exert on Q1 separately and get the vector sum. Okay, so look at this. Let's assume that Q1 is positive. Okay, and let's say Q2 is negative. So F12 is an attractive force given by the red arrow. Now let F3 be also negative, Q3 be negative. So F13 given by the blue arrow is also attractive. Now let us say that Q4 is positive. If Q4 is positive and Q1 is positive, then F14 is going to be a repulsive force indicated by the dark red arrow. So what will be the net force? The net force will be the vector sum of these three. Okay, or F1 will be F12 plus F13 plus F14. That is force on 1 because of 2 plus force on 1 because of 3 plus force on 1 because of 4. Like this you can go to infinity. Okay. So this is your principle of superposition. So let's just look at one numerical where three charges are involved. Where three charges are involved, and let's just work it out. Okay, so what is there in this problem? Let's say you have three charged particles held at rest. That's the first criteria for us. Okay, they are held at rest. And what electrostatic force owing to the other two charges will act on Q1? So you have a charge Q1, Q2, Q3. Q1 is negative, Q3 is negative, Q2 is positive. And their values are also given to you. Q1, Q2, Q3, they're all in microcoulombs. And then the distances are also given to you. I'm interested in one. So R12 and R13 are important for me. I have them with me. Additionally, there is an angle because it's a vector. So we have to have vectors. This is my XY coordinate system. At the origins, it's my Q1. My Q2 is on the positive x-axis. My Q3 is on the second quadrant. Okay. Now I have to get the net force on 1. So how will I write? By principle of superposition, F1 equal to vector sum of F12 plus F13. Okay, F12 plus F13. Next, what I will do is, let me individually find out F12 and F13. F12, let me find out just the magnitude, okay. So what will be F12? F12 will be 1 by 4 pi epsilon naught Q1 Q2 mod, okay, please put mod Q1 Q2 by R12 square. I've already taught you how to do this. Just do it, substitute. Okay, 10 to the power of minus 6. Micro means 10 to the power of minus 6. 10 to the power of minus 6 into 10 to the power of minus 6 will become 10 to the power of minus 12. And then distances are in centimeter, convert them into meters, okay, and then substitute. I have it with me. It is 1.77 Newton. Similarly, I can get F13. That will be 1 by 4 pi epsilon naught Q1 Q3 by R13 square. Substitute. I'll get an answer 2.48 newtons. Next comes the important step. How do I add them? How do I add them? And then, so now we have to look at them as vectors. We have to look at them as vectors. So you can, let me say that this is going to be my I cap direction and this is my J cap direction. You can see that 1 and 2, okay, what is the effect that 2 will have on 1? It will attract. So your arrow should be on the charge that is getting affected, on which you are interested. So you can see that my F12 is an attractive force pulling towards Q2. That is F12. Or I will simply say my F12 is equal to 1.77 I cap. Now look at my F13. Both are negative, 1 and 3 are negative. Therefore, 1 will get repelled. It will get repelled. And it will be along the line joining the two charges. Okay, so this is my F13. And where is F13 lying? It is lying on the fourth quadrant. It is lying on the fourth quadrant. Therefore, this force will have X component as positive, Y component as negative. Okay, so we can write my F13 as I can write it as F13. Okay, so you can see this angle is theta. Therefore, this is going to be, okay, I can make it into two components. I'll use another pen now. I can make it into two components. I can write one component in this direction. The other component is like this. And if this angle is theta, you can see that the X component is going to be the hypotenuse of this triangle. When it's going to be the vertical. Therefore, I will say it is F13 vertical. So sine theta. Similarly, this Y component will be F13 cos theta. Okay. I already know what is F13. So what I will do is I will write it as F13 is 2.4848. Then let me write the X component, I cap component. So it is sine 32 degrees I cap positive. Therefore, I cap. Then minus 2.48 cos 32 j cap. Why did I put minus? I put minus because it is along the minus y direction. So now I have my forces. Okay, I have my forces in the vector form. Now what should I do? I have to simply add them. All I have to do is just add them. So let me just add them. I will get F1 is going to be equal to 1.77 plus 2.48 sine 32 I cap. Then j cap is minus 2.48 cos 32 j cap. Okay, just plug it into your calculator, find out what are the two forces. Then of course you can also get what is the magnitude of this force. Okay, so this is the way you work out numericals whenever you have to apply the principle of superposition. So just complete this numerical on your own, or maybe I'll just if there's no space, so I'm not going to add anything more. So basically, this is how you have to work out principle of superposition problems. So maybe I'll do one thing. I'll just try one more problem for you so that that idea of principle of superposition becomes clearer for you. Okay, numerical on principle of superposition. I'm just going to take a numerical on my own and just do it, okay? Now I'll just take a numerical and do it. So let me say that I have a rectangle, a square. 1, 2, 3, 4. Okay. I'll call this as Q1, Q2, Q3, Q4, and let the distances between them be 2 meters. Let the distances between them be 2 meters, and it is a square. Okay. Then let all of them have the same magnitude. So Q1 is going to be equal to Q3 equal to 1 nanocoulomb. Let Q2 be equal to Q4 be equal to minus 1 nanocoulomb. Find F1. Find F1. So what do you do here? You have to write principle of superposition. So F1 will become equal to F12 plus F13 plus F14. Right? So what will be F12? F12. So 1 and 2. 1 and 2. Let me just use another color. 1 and 2. Yeah, 1 and 2. So it's an attractive force. It's an attractive force. One will get pulled towards 2. It's an attractive force. So let me just draw that. This is F1, 2. Next, what will happen between 1 and 4? Let us see. They are, Q1 is positive, Q2 is negative. So again, attractive force. F1, 4. Now, 1 and 3, it will act along the line joining the two of them, but it's repulsive. So F1, 3. Okay. Now, I can simply show you that F12 will be equal to F14 magnitude. Okay, will be equal to 1 by 4 pi epsilon naught 1 into 1. Therefore, 1 into 10 to the power of minus 12 divided by distance is 2 meters. So 4. Okay. Now, similarly, but what will happen is one of them becomes, so what I will do is I will say this direction is j cap and let this direction be I cap. Therefore, I will get F12 will be, let's say this is equal to some x. Okay. So F12 will become equal to x I cap. And F14 will become equal to minus x j cap. Similarly, I can also calculate my F13. F13 will be equal to 1 by 4 pi epsilon naught. Then the charges are again 1 into 1. So 1 into 10 to the power of minus 12 divided by, what is this distance? What is going to be this distance? So this will be 2 square plus 2 square. So that is 4 plus 4, 8. Under root of 8 is going to be 2 root. 2 root 2 will be the distance. Square of that is going to be, so that's going to be 8. Okay. So let's call this as sum A. Okay. Therefore, I will get vector F13. I will get it as A cos 45. A cos 45. Look at this force. Both of them will be along the positive y and negative x. So minus A cos 45 I cap plus A sin 45 j cap. This A and x you have to calculate. Take out your calculator, calculate, and then add. Okay, that's how you have to work out problems. I'm just doing it in the most general way. It is not even a planned problem. But how to deal with these problems is what I have tried to teach you here. Okay, so I hope I have taken you through the syllabus once. So please study. Don't come to the class without seeing this for tomorrow's class. Okay.